Good evening to everyone. In today's video, we are going to see the working principle behind the JFET. The same question they may ask you the working principle for N channel JFET or P channel JFET. There is no much difference between N channel and P channel except the materials. So kindly go through the working principle of JFET, then you can able to understand what are the main important components behind for N channel and P channel. Okay, so first of all, whatever may be the question they ask, so instead of going directly into the working principle, try to provide a little knowledge about a few statements about your FET device, because it gives an impression that the evaluator can know about the device. Okay, so here I'm providing a few statement that FET is a device which is controlled by the voltage, and the same time in the FET only one charge carriers, the current will be responsible because of the majority charge carriers, so that's why it is called as unipolar device. And based upon the type of majority charge carriers, we know we have the two types of materials, either electrons or holes. If the majority charge carriers are electrons, we call it as an N channel, and if the majority charge carriers are holes, we call them it as an P channel. Okay, so except that majority charge carriers, the rest of the construction or working principle are all the same. So here, before going into it, so I just provide a little diagram about the FET. So this is your FET device. This can be explained when you go through the construction of FET. So this is the FET device. So FET is having three terminals: gate, source, and drain. So here the gate terminals, that means the injected opposite terminal, that means this is the P channel JFET. So the opposite terminal, that is N type of material, is injected into this diffused into this P channel. So here it forms NPN. So these N channels will be joined together to the gate. So these N channels are joined together to a gate. So the opposite end of the P channel will be the drain, and one more end is the source. So we have total three terminals here, and the same time we have the only one channel, and these are the diffused elements. The P type material, N type materials are the diffused materials. And here two voltages will be provided. One is across your gate and source, and one is across your drain and source. Based upon the voltage, you are provided to the drain and source and gate and source, you can get it as a forward bias condition or reverse bias conditions. Okay, so here I'm just go for the working principle of N channel. So totally we having three stages. That is, in the stage 1, whatever the voltage you are applying across your gate and source is simply a short circuited one. And the next one, the drain and source voltage is reverse bias condition. With little amount. Further it can be increased. Before going into the theory, I just show the pictures, then you can able to understand this. So this is the conditions. So initially this is the the majority portion is whatever the conduction path is N channel. This is the N channel. So in this N channel, this P channels, this P type of material is diffused here, some layers. Okay, and we have the three terminals, as I said earlier. initially the drain and source are forward bias condition. The drain and source are in forward bias condition. And the next, gate and source are simply a short circuited. Simply a short circuited. At this moment, the current from the drain, it goes to the source. The current from the drain, it goes to the source. Now, instead of maintaining, a short circuit is nothing but VGS equals to 0. VGS equals to 0. Instead of that, if you maintaining this VGS voltage in reverse bias condition, that means for positive we are providing negative, for negative we are providing the positive. In reverse bias condition, the depletion region, that means the conduction between your P and N, the common point, common layer. So the depletion region between your P and N channels will be increases. Okay, when you apply the reverse bias condition, as we see in this one in your PN junction diode, in the reverse bias condition the depletion region width will be increases. As I said, in this reverse bias condition the depletion region width will be increases. As this width increases, that is the depletion region here, this depletion region width increases here, automatically the channel, okay, the path for your current flow is decreases. Whenever this current path decreases, when this channel width decreases, automatically the current is decreased. As this reverse voltage increases, this depletion region increases. As this depletion region increases, the width of the channel is decreases. As the width of the channel decreases, the current also decreases. Now, instead of smaller amount of VGS, you further increase, you go for higher values of negative voltages. So whenever you go for the higher values, automatically these two depletion regions will touch together. That means there is no further flow of the current from drain to source. This condition we call it as a cutoff voltage. This condition is called cutoff voltage, because there is no further flow of current. When there is no further flow of current, the circuit simply as open circuit. There is no connecting point between your source and drain. This we called it as cutoff voltage. The same thing we just provided here. You can simply go through. Whenever you go through the things, it is easy to understand. So whenever you apply the voltage between your drain and source, the current, whatever the electrons, because here the majority charge carriers are electrons, it is try to flows from source to drain through the channel. Okay, through the channel. So the drain current, the electrons are flows from source to drain, but the drain current is flowing from the drain to source. It should be a closed path, drain to source. Whereas when you go for the gate as a short circuit path, there is a minimum reverse voltage. Between your gate and source. So here there is a depletion region which is very minimum, which is because there is no voltage across your gate and source, it is very minimum. So the conduction path, whatever the conduction channel is, it is maximum. So there is a maximum current flow in the channel. Okay. So as the gate source current is increases in reverse bias condition, this reverse bias condition leads to the increase in the width of your depletion region. So this will reduces the width of your conduction channel, and this reduces the drain current. As you increases further, these two depletion regions will touch together such that there will not be any conduction path between your in the channel. So this will prevent their current flow in the channel. So this is called as an cutoff region, and the voltage at this region we call it as cutoff voltage. The same thing, this is for N region, this is for N region. If you go for the P region, I mean P channel, the same thing will be appears, but the only thing is the material, instead of PNP we can go for NPN, and instead of it is in a reverse bias condition, this will be the forward and this will be the reverse bias condition. A part of that, the way of width reducement or conduction path, current, all the things are same. Okay, I think it will be helpful for you. Thank you.